this closed loop, which is actually a gauge invariance quantity. So then we look at this phase as a function of ky. So if the phase 1 once, then we'll get to number 1. So, and we can use the same method to calculate the Z2 invariance as well. So then, in this case, if the phase winding number is 0, so that's to number is 0. If the phase winding number is 1, then to number is just 1. So this is, then we can generalize it to calculate the Z2 invariance. It's just simply generalize the U1 case to UN case. So then everything becomes a matrix. Then we did this calculation for the TAAS material. So then in the up panel is the mirror to number calculation for this mirror invariant plane. So we can clearly see that the winding number is 1. So that means the mirror to number of this two mirror invariant plane is 1. So then in the up panel, in the lower panel is the same calculation, but for this phase evolution on the two diagonal planes or two glide mirror planes. So then we see that we can clearly put a reference line here where all those phase evolution lines just seem to cross the line. That means the Z2 invariance for this plane is just 0 or trivial. So then we can, from our calculation, we can clearly see that the surface, Fermi surface, must stop at somewhere which generates a Fermi arc. So that we can make sure that there must be a wild node inside the momentum, inside the brane zone. So then the next question is how many wild points are there inside the brane zone. So for that we need to calculate the total flux flow for the 1/8 of the reduced brane zone, 1/8 of the whole brane zone, which is the reduced brane zone. Then from our calculation, we got the total flux flow is actually 1. So then the last step is we actually look at the Berry curvature pattern for each constant KZ plane. And for that, from that we determine all the position of the wild nodes. So then we found that in each reduced brane zone, which is 1/8 of the total brane zone, we got 2 plus charge and 1 minus charge. So the total charge inside this reduced brane zone is plus 1 or minus 1. It depends on which part of the brane zone you are looking at. So then this is so totally there are actually 8 wild points located at KZ equal to 0 plane, and 16 wild points located off the plane. So totally there are 12 pairs of wild points. So I have a little movie so that we can. This is the location of all the wild points within the brane zone. You can actually take a look by, So these are actually the wild points located at KZ equals 0 plane, and there are 8 of them on the up half of the brane zone, and the other 8 on the lower half of the brane zone. Can rotate in 2 different ways. blue will representing two different charges and or two different colors. Yeah, so this is the side view of those wild points and the top view. So I will emphasize that there are two types of wild points. The first one we call it wild node 1. It's a W1 is located near the zone boundary, and W2 is located inside, very far away from the zone boundary. So then from the top view, you will see that these W2, those wild points inside zone boundary, they can actually, there are two wild points project to thin surface points along the 001 surface. So from top view, at this point, there are actually two wild points, one up and one at the lower peak. So then these are the table indicating all the exact positions we found for all the four different materials. We'll see that actually we actually need the separation of the wild nodes as far as possible. That would be good, right? So then from the table we can see that parallel phosphide actually has the biggest separation. So compared to parallel arsenic, the phosphide material, the separation is a little bit bigger. So then we also calculate the Fermi arcs. So I will emphasize that this calculation is based on tight binding calculation, and we did the relaxed charge on the surface. So then we get Fermi arc like this. That's quite clear connection projection point of the bulk wild node. So the lower panel is the Fermi arc side. So then actually after that, the archive group in IoT, actually Hongding's group did the archive measurement on that. And the Fermi arc pattern is actually quite different from our calculation. So and then this is because this material has no inversion symmetry. So once you generate a surface, the surface will have to relax the surface charge. So then it's not a layered material. So the surface charge relaxation is very important for us to get the right shape of the Fermi arc behavior. So then we did this first principle calculation with full relaxation on the surface charge on the surface. Then we get very consistent results with their RF measurement.